So first of all, good morning. Thank you for coming to join us. Thank you for listening to me speak and giving me an opportunity to sort of share the mission of MLCommons and what we aim to do with the MLPerf family of benchmarks. So this is an overview of my presentation. We'll first start with the organization and benchmarks, and then do a deep dive into MLPerf client and storage. MLCommons is a nonprofit. We're an industry consortium. We are focused on making AI better for everyone. And as you can see on the right, what that means is we want to make AI more accurate, safer, faster, and more power efficient. Right? Every day we are seeing in the news, this week in particular, as was discussed earlier this morning, right, the excitement of getting a new AI model that has faster capabilities or better capabilities, and how this all promises to transform society in remarkable ways. Whether it's the self-driving cars that are buzzing around San Francisco that I get to see every day, or better AI for medicine, or better translation. MLCommons is an organization that we're powered by our members and by the broader community. We have over 100 members spread all across the globe, over 125 in fact. We're on 6 out of the 7 continents. If you know of any IT companies, any folks active in AI in Antarctica, 7 out of 7 is always better than 6 out of 7. So please reach out. Maybe someone at McMurdo Station needs to get some systems for training and inference. One of our premier projects is MLPerf. We've got tens of thousands of performance results. MLPerf is the open industry standard for measuring the performance and efficiency of AI, and that's what we'll be talking about today. So I guess to start and motivate, many of you in the audience may be, if I can be forgiven, professional skeptics, right? And so I see some nods. That's good. That's good. Yes. Right. So why do we want, and why are we building benchmarks as a way to make AI better? Like, what is that going to do for us? And I like to go back to the aphorism of Peter Drucker up here, that if you can measure things, you get improved, right? And we've seen this when we're writing online, right? You can A/B test your headlines and see what is attention grabbing. Does adding images work or does it not? What should we be doing? Do we need a new screen? Has Screeny the first, maybe needs to be a bit better, right? So once we start measuring these things, we get to improve them. And this is really the image that, to me, captures the real goal of benchmarking, which is we're in this as a community, as customers, as researchers, as buyers, as sellers, all working to make AI more capable, more efficient, and we go farther together. If you've ever gone canoeing or kayaking or in crew, when you get the whole team in harmony, you just fly across the water at incredible speed. And that's our goal. How do we bring the community together and align on what does it mean to be better? Right? That's the point of a benchmark. Right? It gives us a true north to guide towards. And we want them to be, in order for them to drive this progress, right, to help us get forward, right, we want transparency, and we want to be able to again, move faster. And a benchmark, no benchmark is perfect, right? Again, for everyone in the audience, right? We're trying to get to north, but if we're 5-10 degrees off, that's okay, because we're all going together, we'll course correct, and we'll go more rapidly. So the reason behind this, this is what I like to call sort of my TED Talk slides. There was a great paper from Baidu, last decade, that really talks about why we want big data for AI. And this drives into our needs for compute. And so really what they did is they looked across many different modalities of AI, And what they found is that when you don't have enough data, AI isn't actually that useful. Just talk to an expert, make a good guess. But what this chart shows is on the x-axis, you've got the data set size. On the y-axis, you have error. Lower error is better, right? And so you start out in this small data region where the error is high because you don't have enough data. But when you start getting enough data, the error starts dropping a lot. The accuracy goes up tremendously. And somewhere along that curve is, going from lane warning to lane following, to staying in the lane, to start following the car ahead of you. It goes from, a sort of jokingly good translation that you'd never really want to show to everyone else to, I'm on the streets of Singapore and I just, can use Google Translate, right? And those are all going to be points along those curves. And so as we drive up the amount of data, we get new capabilities that are, truly amazing.
David, what's the proof for irreducible error?
Well, the proof for reproducible error, I guess in theory, maybe there is no irreducible error, but I'm going to claim that no one can see the future. Like no person, no AI. And that's in some ways what that's saying, right? Which is it doesn't matter how much data we feed into a system, right? There's always some things you can't predict.
I mean, there's obviously a limiting factor here. As you get more and more data, there's less and less improvement, but that doesn't mean that.
Well, right, at some point it's going to saturate. And that's really what this is saying is, but we're clearly in this power law region, right? Like many of you may have heard of the scaling laws that OpenAI has popularized about how we build bigger and bigger networks with more and more data. That's in the power law region. So the consequence of this is that in order to learn from all that data, we need bigger models. So this is some data from Rise Lab, again, time on the x-axis, and the size of the networks is on the y. And what you can see, and this data is a few years old, but what you can see is it's just up and to the right? We're seeing transformer-based models growing at 250x every 2 years. Right, and the transformer is the fundamental building block that we see behind things like ChatGPT, DeepSeek, et cetera. And so what that means is our compute demands are growing even faster, right? The compute is in some ways both the product of data and model size. You make the model bigger, you now need to learn from more data, and this is even growing even faster. Again, not 250x, it's 750x. So the need for compute is tremendous and insatiable, is really the point I'm making. And so you put all this together and sort of here's what I like to call the fundamental theorem of machine learning is big data plus a big model plus big compute is innovation, right? When we put this all together, right, we get things like better cancer detection, cars that are safer on the road, safer than me, safer than all of us. And I look forward to that future. Ultimately, machine learning is a full system problem. So, and we're going to get to talk about some components of that system today, in particular, certain compute and storage. But when you look at training these models and increasingly doing inference, there's so many factors that come into play. And so that's both good and bad, right? It makes building a benchmark hard, but it also means that we have so many different levers to pull to improve performance, right? There's the data itself. Sometimes it turns out if you sort the data cleverly, you can boost performance by 20, 30%. There's the silicon technology we have. Folks like Intel, TSMC are hard at work improving that, and that gives us more performance, more transistors, better architectures, better algorithms, whether it's more efficient training or maybe a better fast Fourier transform. Better code generation, better compilers, better drivers, those contribute as well, and larger scale, right? Once a long time ago, it was very common to see people training on a workstation, a small system, maybe a few processors, and now we see the most cutting edge models are using hundreds, thousands, tens of thousands of accelerators. And so all,
David,
yes,
I'd just like to throw out here for our viewers and what they're probably thinking, the elephant in the room of the last week or two, which is, of course, DeepSeek,
yeah,
is challenging an awful lot of these assumptions about how much compute you really need to do to, get really good models. So I'm not asking for any sort of response from you now, but I'm sure a lot of people are thinking about this as you're going through these benchmarks. Do we really know what we thought we knew?
right. Well, and I mean, I think it actually really highlights the point I'm making here that, to really accurately understand performance and what's going on, you need to look at all of these factors, right? Yes, we do need massive compute. And even if you look at like what DeepSeek did, it involved a tremendous amount of compute. But part of what they were showing is being clever and getting it right can really reduce the needs of compute, right? That was one of the takeaways. And part of that is going back to that. If you pick the right algorithms, the right tuning, the right architecture, the right optimizations, you can use your compute a lot more efficiently. So
when you talk about measuring it, just maybe just really quickly, we talk about measuring it. The paper by Emily Bender et al. On can language models be too big? Really recommend also measuring the impact to the environment and to people and the rest of it. So, are we going to talk about that at all?
So peripherally, yeah. And so, I mean, the thing I would say is, so I helped lead MLPerf power, and that is the industry standard way of measuring the power efficiency, right? And so, I think the point is, as we look at deploying any sort of new technology, we want to look at the broader impact it has, right, on the environment and other places. And being efficient with our AI is critically important, right? And so, we're building the tools to help everyone measure what is the energy efficiency of training and inference for AI, and that's critical. And I couldn't agree more that is important. I spent many years, working on that.
Very cool.
So the MLPerf benchmark suite is designed to help us measure performance, to help drive the industry forward, to help us understand, what is the fastest solution? Not so we can beat up vendors, although we do a bit of that, right? Or I should say we don't, but people do, but to help really align buyers and sellers and understand, right, are we getting the right thing for what we want to do, right? It's a tool, it's about information. So that means some of the goals of our benchmarks are, we want the performance that we measure and the energy efficiency that we measure to be reproducible, right? If you can't reproduce if I tell you that I managed to jump 50 feet in the air, but it was in the room the other day, you might not believe me. In part, seems unlikely I can jump 50 feet in the air. But, if I tell you, hey, here's how I did it, I said, big trampoline, and then you try it and you do it, makes sense, seems reasonable. And so we need the replicability to establish trust and to really build useful tools, right? You want to be able to know that what the vendor is claiming actually can be done, or what the researcher has achieved is not just a fluke.
And ultimately, even if it's not always done, knowing that it could be done hopefully keeps people from making ridiculous claims about their models. And that's sort of an endemic problem to the AI space, because we're talking about such huge systems, so much hardware, so much data, such an incredible importance of software and tuning and optimization, that we need them to know that somebody's going to hold them accountable if they're making ridiculous claims about the performance of their system.
Yeah, and that's one of the things that I was looking at when I was looking at their slide is accountability and auditability of the results are a couple of things that I would like to see come out of this.
Yeah.
That the idea that you can actually come up with the source material. You can't just say you jumped 50 feet in the room somewhere, but you can actually say, here's a demonstration of me jumping 50 feet.
That's right.
And the auditability of, I got this result, but can I actually go back and find the source material that gave me this result?
Yeah. So, and that's great points. I mean, so that is built into our benchmarks. There's peer review. So, everyone who does a benchmark, they're all in a room looking at each other's results. And,
It's not just peer review. It's the ability to actually have an audit trail of,
yeah.
you have a result, where did this result come from?
And what are the artifacts used to produce it? All of our benchmarks, when you submit the submission, not just the logs, not just the results, but like the things that you need to reproduce it all end up in GitHub. And so actually, getting back to your point, one of the things that's great about that is it means that your recipe, your best known method, is now public. And so your customers can see it and they can say, aha, that's how I tune things. Let me go do that. Or, maybe I can't quite tune things that way because, my systems aren't set up, right? Maybe I've got 2 data centers that are talking across a large distance and that's not what they had, but I can see how to adapt it, right? And so that transparency, that visibility, that traceability, and in fact, having audits, which we do on some of our benchmarks where it makes sense, is vital for that. And so we want our benchmarks to be representative.
Can I ask a question about the audits? And I know more about like performance or task-oriented benchmarks like SWE-bench and things like that.
Yeah.
As opposed to some general performance benchmarks.
Yeah.
I find in the task-oriented ones, particularly like SWE-bench and stuff like that, the logs don't really tell how they train to train or teach to train. There's sort of the bias that the models. There's this whole discussion about the benchmarks are flawed. I agree with Stephen that they're valuable and they're what we have, but a lot of the models are training with the benchmark data in mind. And when I look at the logs of the task-oriented ones, I don't see beyond. I don't see the depth of how they were I can't see how they taught to train to be able to achieve the benchmark results that they did. And I don't know if that question makes sense or not, but
so yeah, so the question.
the auditability is suspect, even with logs and the GitHub.
I think that's actually an intrinsic challenge of measuring, right? As you say, task accuracy is what I would say.
Yeah.
And that's a really, really tough thing to do, right? That's actually not what we're doing with MLPerf. What we do is we establish a required level of accuracy. And if you pass that,
Got it.
then you have a valid submission. And then
I was just wondering if those characteristics, because you do have model guard and like, are you going to talk about any of that?
That's a different part of
Okay, all right.
what's going on. So as we build these benchmarks, because of what we mentioned, right, the having the reproducible artifacts being a best known method, we want all of our benchmarks to be representative of real use cases, things that people are commercially doing that are impactful, right? So this means, we end up actually having to retire benchmarks pretty often. There's a very rapid cadence.
Could you give some color? So we deprecate or we retire a particular benchmark.
Yeah.
What are some of the key characteristics that would say this benchmark is really no longer fit for purpose? Is that a function of the industry, the landscape, or where the technology has moved?
All of those factors come into play. I'll give you an example from some of the earliest days of MLPerf. When we started out, we had 2 machine translation benchmarks. Same task. One was transformer-based and one was using RNNs. And when we started, RNNs were really what people used in production, but transformers were pretty new and they had promising results. And there was a sense that they were much more likely to scale into the future. And so we said, okay, we're going to have both of them. But fairly swiftly, we ended up retiring the RNN, in part because transformers proved to be so much better that everyone in the industry just switched to that for that particular task. Now, there are other places where RNNs are still used. Today, they're oftentimes used on time series data, on speech stuff. But ultimately, we want to be representative of what people are doing in production, although we also need to lean in and lead a little bit, right? There's a spectrum of production uses, and you don't want to be too far back. You don't want to be too far forward, right? And so it's dialing that in, talking to customers, talking to heavy users, talking to industry, and then looking at, is it still a good benchmark?
So to simplify it into like a 1, 2, 3. So is the goal to be more associated with the pioneers, associated with the settlers, or what would be the laggards?
Going Wardley on us.
I did go Simon Wardley on you there. So
I think for MLPerf, for a lot of what it's a little bit different for training and inference, right? Inference is fundamentally about production.
Yeah.
And so I think for training, you have to lead a little bit more than inference. But I would say you kind of wanted to be weighted forward, because part of this is we're illuminating for the whole community, like what's important and what's going to be important, right? I would say, ultimately, actually, even some of the retired benchmarks are still useful, but maybe more for some of those lagging cases. So I think the interesting thing is, I think over time, any given benchmark will pass from your, stages, and we want to pick the right point. And so it's when we introduce a benchmark, it should be a little bit leading. For example, when we introduced GPT-3 as a benchmark, GPT-3 was already out, but we followed very, very quickly. And again, we have to do everything open, transparently, et cetera. So, and what this gives us is, we get to help improve the state of the art, right? By making fair and useful measurements. Right, and so the use here is, of course, as it goes from, out on the cutting edge, performance starts improving, and eventually it might saturate, right? But, helping to drive that flywheel is critical for us. So I want to talk about the overall MLPerf family. So we started with MLPerf training. That was the one that got us started in 2018. We moved into inference, both data center and edge, mobile for smartphones, tiny for IoT devices, storage, which we'll get to talk about, client for sort of Windows and Mac and desktop, laptop machines, and then automotive. So there's been tremendous growth and expansion of breadth. Really, as ML has begun to touch everything.
So David, there are a couple other benchmarks that are not on this list, Illuminate and AlgoPerf. What's the distinction between MLPerf benchmarks and non-MLPerf benchmarks?
Yeah, so I that's a great question. So I think MLPerf, the way to look at that is that's really focused on performance and efficiency. AI Illuminate is focused on measuring a very specific quality that is sort of the risk and responsibility. Essentially, is your model sort of doing as you intended? Is it a chatbot? And if so, is it wandering off and recommending what car to buy, or is it really sticking to the task at hand? Things like that. And AlgoPerf is focused on the algorithmic performance. So that's focusing on just one aspect of training, not the whole end-to-end thing. It's looking at, are there better algorithms, for example, than SGD? And so, one of the great things that came out of AlgoPerf was renewed interest in a technique called shampoo, which is a different high-level optimizer for training. But MLPerf is maybe a little bit more hardware-centric and very much performance and efficiency. And over time, as we've grown, we've really gotten to improve the not just the breadth of the MLPerf suite, but the depth, right? We've have, as you asked about earlier, we added power measurement for inference and tiny first. Then we added power measurement for training in cloud systems. So, you could actually, if vendors were interested, you could measure the power efficiency of training in the cloud and then compare it to an on-prem system.
How do you measure power? Do you actually do it algorithmically, or are you doing a?
So for MLPerf inference in smaller systems, the preferred methodology is essentially a power meter. So you're actually measuring the power that is consumed. For some of the larger at-scale systems, like you might find in MLPerf training, where you got dozens or hundreds of nodes, you're measuring power of the compute, and then there's certain portions that are either estimated or measured. But in general, we tend to favor full system measurement.
Okay, and are you including cooling?
Full system. So if if your system is on the wall, if you plug in the system, you've got fans running, you choose to run them on high, that would be part of the.
Well, but you're not taking into account where you actually dissipate the heat that you're generating to?
At the full data center scale?
Yes.
So
I mean, you need environmental cooling, or you need some sort of cooling method to dissipate the
yeah,
heat.
so it's not going to measure if you're in a data center. It
Okay,
may not measure.
I think you've answered the question. Okay.
The outermost cooling loop.
Okay, yeah.
So I want to talk about what we've managed to accomplish in and with the broader community. And so this is my favorite chart to share. And so again, on the x-axis, we've got time. On the y-axis is performance on a log scale. And there's this solid blue line along the bottom of the screen, and that's Moore's law. We all know that. That's right, the increase in transistor density per unit area of silicon. Maybe a little bit more complicated than that, but it's about transistors. And if you assume that every transistor linearly translates into more performance, that blue line is what you would get. And each one of those colored lines above it is a benchmark from the MLPerf training suite. So the dotted lines are for ones that are discontinued. The solid lines are ones that are still with us. And so what you see is that if you compare the best performance on any MLPerf benchmark, right? This is not a, hey, let's go find a weak baseline. This is, let's get the best submission in every single round on every single benchmark and compare them over time. What you see is that we're beating Moore's law. We're ahead of the curve by, sometimes up to 10x. And
the biggest challenge, David, with this chart is that some of those benchmarks run on 5 GPUs, some run on 2,000 GPUs. So, I mean, over time,
that's right.
The amount of hardware that's been associated with these runs has increased considerably.
Yes, that's actually designed into the benchmark, right? Because as a customer, right, if you look at what folks are doing, they are using larger and larger systems because it gives them the ability to solve bigger and bigger problems, right? And so, and I said this up front, which is scale is an intrinsic aspect of machine learning. Now, you're right that many of these systems are larger, and that is absolutely a capability that customers want, customers need, that does drive innovation. And so it, from my standpoint, it's absolutely fair to measure that. Right, and what we see is that, in aggregate, the performance that we've seen improve in some cases is 50x. And you're right, some of that is through scale, through moving from, maybe one node up to dozens. Some of our largest submissions are thousands of accelerators, but it takes truly dedicated hard work, algorithmic innovation, all sorts of optimization to get a workload to scale across multiple systems. So this is a strong scaling benchmark. We don't increase the size of the data set. So when you are able to use more machines, like that's actually very significant. There are a lot of benchmarks where they just expand the size of the data set and it will scale to larger and larger systems. That's not true of MLPerf training. So when you see, hey, we're able to use more machines, that actually is truly valuable to customers and represents, pushing forward.
The other thing are obviously the efficiencies of the software have changed over time. Going from floating point 64 to floating point 8 or whatever has also impacted how much these sorts of benchmarks can run and train.
Yeah, absolutely. And that's something we want to measure, right? Because again, it comes back to, is this useful on the real problems that we're looking to solve, right? And one of the things that is exciting is when you see someone come in with a new numerical format and say, hey, we got this to work. And sometimes what'll happen is, and it's been very exciting, is sometimes they'll come in and they'll say, okay, we're using this new numerical format only in some places. And then 6 months, a year later, they say, actually, we're able to now use it everywhere because we made our software better, right? And so, again, if it's a customer valued, if it's an intrinsically useful thing, right, we want to be able to measure that.